net case reproduction number. So then, it is also called the R number. Now, it is quite a bit different from the R0 that we've covered beforehand, where the R0 was the potential or the most extreme outcome for that disease, where every individual is susceptible. However, the R number is used to measure the transmission of a disease in a population, where the population includes individuals who are susceptible and non-susceptible. It follows the same pattern with if the R number is 1, then the disease is population. If it's greater than 1, it's increasing the population. Less than 1, then it's decreasing the population or dying out. So it is exactly the same in that sense. However, I would like to note that the R number is, more often than not, is going to be lower than the R0 because it's taken into account the non-susceptible. So then, let's give you some visual aid here, and I've got green being immune and blue being infected. Now you'll be able to go and see that the R number is just when you're taking the immune or non-susceptible into account, you're taking that into account when you're counting them. So this individual was only able to infect one person, so that's 1 plus this other person. That person was only able to infect one individual. So divide by 2 to go and get the average. The R is 1. R number is 1. This means that it is stable in the population or endemic. Right then, let's go and have another example. Now this individual was able to go and transmit to 2. This, another 2, and this 3. So we divide it by 3 to go and get 2.3. So the R number is 2.3, which is an exponential rise in cases. Correct? So, for the calculation, you can go and calculate the R number from the R0 number. And you can do this by timesing it by the proportion of the population that is susceptible. Now you do this by taking the average life expectancy of a population and then the average age of an infection in the unvaccinated. That goes and gives you the proportion susceptible. That is the average age of infection in unvaccinated divided by the average life expectancy of the population. So, plug in the numbers. Let's say in this example, in this population, and by the way, in this population we're assuming there is no vaccine and the disease causes lifelong immunity. Now this is important. It causes lifelong immunity. So once you've got it, you're not going to get it again. So, life expectancy is up to 92. And the average age of infection in the unvaccinated is 6, meaning the average individual is going to be immune from 6 years old. Correct? So, the only proportion of the population that is actually able to be infected are the under 6-year-olds. So, we do our proportion here, and it's 6 divided by 92, which is 0.0652. This means that 6.5% of the population is susceptible. Correct? Now what about the R0 number? Now remember beforehand, in the previous video, we calculated it from the secondary attack rate. Now, there is a far more comprehensive way to calculate the R0 in this case. And I said that it was complicated. This is the next generation matrix method for calculating the R0. As you can see, it is heinously complicated, but I'll give you a brief summary as to what it is including, because it's subcategorizing groups for risk, and it is doing that by taking into account those who are asymptomatic but still shedding, etc. So it's a far more comprehensive and way of calculating the R0 number that is very, very likely being used in this current COVID-19 outbreak. So I will do another video on the next generation matrix method for calculating the R0 in a separate video, because that is quite complicated and you're gonna it'll take quite a bit of time to go and actually go through it all, but that at the moment in its base form is the net case reproduction number, or the R number. Thank you for listening.